All right, let's finish up section 6.6 on inverse trig functions. We had only gotten through number 12 yesterday. We saw under what circumstances we could say arcsine and sine just undo each other. And when we had to say, well, arcsine and sine can't undo each other here because 2/3 pi is not an answer that inverse sine can give me. Well, on number 14, we definitely cannot say sine and inverse tangent undo each other. They're not inverses of each other. So how could we evaluate sine of inverse tangent of square root of 3? Well, I can tell you that it is similar to what we did in number 12, part A. Even though I knew 2 pi over 3 could not be the answer, I could find sine of 2 pi over 3 and then find an angle whose sine was that same value. On number 14, I can find the angle whose tangent is square root of 3, and whatever that angle is, I can take the sine of that angle. So again, I have to think about inverse tangent always gives me an angle between negative pi over 2, positive pi over 2. And if inverse tangent is positive in one of these two quadrants, it's the first quadrant. I'm looking for the first quadrant angle where tangent is square root of 3, or the y divided by the x is square root of 3. I know it's either going to be pi over 6 or pi over 3. I just have to figure out which one, if I divided the y coordinate by the x coordinate, would end up with the square root of 3 on top. You may be able to squint and do that. I need to write the ordered pairs and say at pi over 6, the y divided by the x would leave me the square root of 3 in the denominator, and that's not what I want. So pi over 3 is the ordered pair a half square root of 3 over 2. That y divided by the x would flip the x, the 2's would cancel, and that would leave me just square root of 3. So the angle whose tangent is square root of 3 is pi over 3. Then I just need to find sine of that. Sine of pi over 3 is the y coordinate at pi over 3 radians, and that's square root of 3 over 2. Again, I just had to evaluate or find the angle whose tangent was square root of 3, and once I identified that angle, give the sine of that same angle. The B part, I'm looking for the cosine of the inverse sine of 0. Well, first I need the angle whose sine is 0. On the unit circle, where is sine 0? At 0 radians and at pi radians. Which one of those can inverse sine give me as an answer? Remember, inverse sine only gives me answers between negative pi over 2 and positive pi over 2. So the angle whose sine is 0 in this interval is 0 radians. So I'm looking for cosine of 0 radians, and cosine of 0 radians is the x coordinate of this ordered pair at 0 radians. Cosine of 0 is 1. So the cosine of the angle whose sine is 0 is 1. In the C part, I'm looking for the angle whose cosine is 0. That's the angle whose x coordinate is 0. That either has to be at pi over 2 or 3/2 pi. It has to be on the y-axis because that's where x is 0. And if you think about what cosine, inverse cosine can give you as an answer, inverse cosine has to give you something between 0 and pi. So the answer to inverse cosine of 0 is pi over 2. And now we need the tangent of pi over 2. And we know that half pies are where tangent, or odd half pies are where tangent has its asymptotes. So tangent of pi over 2 is undefined. We found the angle whose cosine is 0, and then we found tangent of that angle. Now, what's different about that and number 16? Number 16 looks similar. I could find the angle whose sine is -2/5, or could I? Is that something I have memorized on the unit circle? Do I have one of the angles that I have memorized? Do any of them have the y-coordinate -2/5? No, they don't. So we've done something similar to this before. We've said, I don't know the angle whose sine is -2/5, but I could draw a picture of it. I could draw a fourth quadrant angle. Has to be fourth quadrant because inverse sine has to give us an answer between -pi over 2 and +pi over 2. So here's my fourth quadrant angle whose sine is negative, and I want to raise a vertical line up to the nearest x-axis and say, well, let's just call this guy U for ugly, because we don't know what that angle is. But we can say if U is the third quadrant angle whose sine is -2/5, the definition of sine says 2 has to be your opposite, and 5 has to be your hypotenuse. And in the fourth quadrant, the y is negative. So even though I don't like to label a side of a triangle negative, I'm saying the coordinate of this point would have y being -2. And the hypotenuse is 5, and I can use the Pythagorean theorem to find that adjacent side. The adjacent side would be the square root of 25 minus 4, or the square root of 21. So now, even though I don't know the degree measure or the radian measure of U, I can still find cotangent of U because I know the definition of cotangent. Tangent is opposite over adjacent. Cotangent is adjacent over opposite. So if I call this angle that I was looking for U, I can say the cotangent of U is adjacent over opposite, and I'm just going to put that negative out front, negative square root of 21 over 2. Similarly, on the B part, I don't have memorized an angle whose tangent is 7/4, but I can draw a picture of an angle whose tangent is 7/4. And because tangent is positive, I know that that must be a first quadrant angle, because tangent in between -pi over 2 and +pi over 2, the only place tangent is positive is the first quadrant. So I'm going to draw a first quadrant angle, label it U, and I'm going to label the sides of that triangle in such a way that tangent is 7/4. Definition of tangent is opposite over adjacent. So for this angle U, I'm going to drop a vertical line down to the x-axis and say the side opposite U has to be 7. The side adjacent to U has to be 4. And that means the hypotenuse has to be square root of 49 plus 16, or square root of 65. I don't know the degree measure or the radian measure of this angle U, but I can find secant of U. Because secant is the reciprocal of cosine. Cosine would be 4 over square root of 65. Secant would be square root of 65 over 4. And then the C part, it's so much the same, I'm just going to skip it. I need to draw a picture and label an angle whose cosine is 1/5. Once I get my triangle drawn, I can find cosecant of that angle. Let's go on to something a little bit different. Number 18 may be the ugliest problem I've seen in my life. The sign of the quantity, I'm saying quantity because it's sign of this big old thing, the sign of the quantity inverse sine of 5/13 minus inverse cosine of -3/5. Does that look like anything we have seen in the past week? Does it look familiar at all? I know this is some angle. I could call it, let me see what I want to call it. I'm being sneaky here. Let's say I'm going to call this angle U. I don't know the degree measure of the angle U or the radian measure, but I could draw a triangle just like I did on the previous problem and label some angle U whose sine is 5/12. And this is a different angle. This is the angle whose cosine is -3/5. I can call that angle V. Now does it look like something you've seen before? How about sine of U minus V? That's exactly what we have. I need to draw both of these triangles so that I can extract the values that I need to use in the subtraction formula for sine. So here's my angle U. It's in the first quadrant because inverse sine is positive in the first quadrant, or the angle whose sine is positive is in the first quadrant. I need to label that triangle in such a way that the opposite side is 5, the hypotenuse is 12, and that means the adjacent side would be square root of 144 minus 25. That's square root of, is that 100? I don't think that's 116. 144 minus 25. 119. I didn't remember that being an irrational number. Let me just double check it. Opposite over hypotenuse, 5/12, square root of 144 minus 25 is 119. I don't know why that number's not ringing a bell as if I've ever seen it before. but that's the side adjacent of the angle U. Then I need to draw an angle whose cosine is -3. I just wrote on it and I can't tell what was there before I wrote. I'm going to guess, I'm going to play like that's a 5, -3/5. If it's not a 5, then just change it on your paper and do this problem like it was a 5. In what quadrant would inverse cosine give me an angle whose x-coordinate was negative? Remember, inverse cosine is going to give me an answer between 0 and pi. So if the x value is negative, this must be a second quadrant angle. So I'm just going to draw a second quadrant angle, not to scale at all. I'm going to label this angle it makes with the x-axis V, and then I'm going to drop a vertical line down to the nearest x-axis and label that triangle in such a way that adjacent is -3, hypotenuse is 5, and that means opposite has to be 4 by the Pythagorean theorem. I think I just figured out why that was bugging me. That's a 13. I shouldn't have written on my paper where I couldn't see. If that's a 13, and I label this 5 and 13, then 169 minus 25 is 144. That's what I thought. I've never seen that 119 before. Square root of 144 is 12. 5, 12, 13 is a Pythagorean theorem. All right, I feel a little bit better about that now. We're ready to use the subtraction formula for sine, and I'm just going to write it down here so we can look at it. Sine of U cosine of V minus cosine of U sine of V. And I'm going to extract each of these 4 values from these 2 triangles. What would the sine of U be? Well, here's my angle U. Sine is opposite over hypotenuse. Sine is 5/13, which we knew because inverse sine was 5/13. Cosine of V, here's my angle V. Cosine is adjacent over hypotenuse, so cosine of V is -3/5. Minus cosine of U would be adjacent over hypotenuse, 12/13, times sine of V would be opposite over hypotenuse, 4/5. You should be able to clean that up pretty easily. That's negative. I would cancel my 5s, but if I did, I wouldn't have a common denominator so that I could add. So I'm not going to cancel my 5s. I'm just going to call that -15/65 minus 48/65 is -63/65. So without knowing what angle U is or what angle V is, I could still find the sine of U minus V using the subtraction formula for sine. All right, if you use that one as an idea of what to do on the C part of number 18, it's going to basically be the same. I could call this my angle U and this my angle V, and draw a picture of angle U and a picture of angle V, Or it may be easier than that. Can you think of anything in the C part that makes it unnecessary for us to have to draw those triangles? I couldn't squint hard enough to tell you the angle whose sine is 5/13, but can I squint hard enough to tell you the angle whose cosine is 1/2? That would be in the first quadrant. And in the first quadrant, x is 1/2 at pi/3. And y is 1/2 at pi/6. So I don't need to draw these triangles because I can identify the radian measure of these two angles. You could use the subtraction formula for tangent now, but which would be easier? The subtraction formula for tangent, which is right here, or just saying pi/3 minus pi/6 is pi/6, and tell me what tangent of pi/6 is. Pi/6 near the x-axis, where x is √3/2 and y is 1/2. So what is tangent of pi/6? The y divided by the x would flip the x. That would make the √3 in the denominator, and the 2's would cancel. That's probably not in the answer in the back of the book, because they probably will have rationalized it and will have written that answer as √3/3. So just understand the difference between these two problems is here I could tell you what these two angles were. Here I couldn't tell you what these two angles were, but I could draw them. All right. What about number 20? Does it look like anything we've seen before? Anything maybe that's at the top of your 6.4 notes? Inverse tangent of 5/12 is some angle. I can call it U, and I don't know the angle whose tangent is 5/12, but I can draw a picture of it. It has to be in the first quadrant. None of my angles are to scale. But let's say there's this angle U in the first quadrant, because inverse tangent only gives us answers between -pi/2 and +pi/2. And the only quadrant in that range that has a positive tangent is the first quadrant. So my angle U's in the first quadrant. Definition of tangent tells me 5 has to be the opposite and 12 has to be the adjacent. So the side adjacent U is 12 units. The side opposite U is 5 units. And that means the hypotenuse is square root of 144 plus 25. That's square root of 169. And that's 13. So even though I couldn't tell you the angle whose tangent was 5/12, I could draw a picture of it. This expression then is sine of 2u. And sine of 2u is the only double angle formula that I use enough to have it memorized. Sine of 2u is 2 sine u cosine u. And I can read sine u and cosine u right off of that triangle. Sine u is opposite over hypotenuse. Cosine u is adjacent over hypotenuse. Just multiply straight across, and you have the sine of 2 inverse tangent of 5/12 is 120 over 169. All right, we have one more of these before we have my second most favorite problems in the book. My first most favorite problems in the book were those simplifying expressions from calculus in section 1.3. They required every bit of algebra that you've ever learned. And just after we do 22, I'll tell you why these last 4 examples are my most favorite, second most favorite problems in the book. All right, that looks like tangent of 1/2 of some angle, and it's some angle that I don't have memorized on the unit circle because none of my x's or y's have 40s or 9s in them. So I'm just going to call that some angle u, and I'm going to find the tangent of 1/2 u. I need to draw a triangle. It's going to be in the first quadrant because that's where between negative pi over 2 and positive pi over 2, first quadrant is where tangent's positive. So here's my generic first quadrant triangle with some angle u, whose opposite side is 40 and adjacent side is 9. 40, opposite 40, adjacent 9, that's tangent. So what about that hypotenuse? The hypotenuse would have to be the square root of 40 squared is 1600 plus 9 squared is 81. It would be nice if that was a perfect square. How about that? It is. 9, 40, 41 is a Pythagorean triple that you don't see very often. Now I need the formula for tangent of 1/2 u. And copying that right off of my 6.4 notes. Remember, that was the formula that we had 2 different versions of. We should get the same answer whether we use this one or this one. Eeny, meeny, miny, mo. I'll just use the last one. I'll use sine of u over 1 plus cosine of u. Sine of u is opposite over hypotenuse. Cosine of u is adjacent over hypotenuse. You can punch that on the calculator if you had to. I would be so tickled if you didn't have to. If you could just say 1 is 41 over 41, and 41 over 41 plus 9 over 41 is 50 over 41. And then the way that you divide one fraction by another is to multiply the numerator times the reciprocal of the denominator. That's just 4/5. If we had used the other formula for tangent of 1/2 u, we might have gotten a different looking answer, but it still should have simplified to 4/5. All right. Last thing in 6.6, and closing in on the end of pre-calculus. Let's talk about these problems that say, write the expression as an algebraic expression in x for positive x's, x's that are greater than 0. Now, this looks like some of the other problems that we've just done. I'm looking for the angle whose cosine is x, and I don't know what that angle is because I don't know what x is. But I could still draw a picture of an angle whose cosine is x, and if x is positive, this angle is going to be in the first quadrant. So I can label that some angle u, and I can draw an angle u in the first quadrant, drop a vertical line down to the nearest x-axis, and then label that triangle in such a way that its cosine is x. Well, I'm used to the trigonometric value usually being a fraction, like 40/9. So I can see opposite and I can see adjacent. Here, x is not a fraction, but I can write it as a fraction. And I can say the definition of cosine tells me that x is the adjacent side and that 1 is the hypotenuse. Because cosine, or the angle whose cosine is x, has the adjacent side being x and the hypotenuse being 1. And what does that make the side opposite angle u? Well, you still figure it out with the Pythagorean theorem. The Pythagorean theorem would give us the opposite side is the square root of the hypotenuse squared minus the adjacent side squared, or 1 squared is still 1 minus x squared. So just like in 22, we have a first quadrant angle, we have all 3 sides labeled, and now I can find tangent of that angle u. Tangent of u would be opposite over adjacent, or square root of 1 minus x squared over x. That's one of the coolest things I've ever seen. This pretty gnarly trigonometric expression that involved both tangent and arc cosine can be written as this algebraic expression, square root of 1 minus x squared over x. And in calculus, it could be very helpful to write this trig expression as this algebra expression, because whatever find the derivative means, I'm pretty sure I'd rather find the derivative of algebra than trig. We can't always change trig to algebra, but when we can, it's a very useful tool. It's a very helpful thing in calculus. All right. We have 3 more. Number 26. I don't know the angle whose tangent is x over 2, but I can call it some angle u, and then I can draw a picture of an angle whose tangent is x over 2. If x is positive, that would be a first quadrant angle again. A first quadrant angle named u, such that opposite is x and hypotenuse, no, I'm sorry, this is tangent, adjacent is 2. Opposite is x, adjacent is 2. What would that make the hypotenuse? Square root of leg squared plus leg squared. You could either write it square root of 4 plus x squared or square root of x squared plus 4. Same thing. And now that I have all 3 sides of that triangle labeled, I can find the cosecant of this angle u. Cosecant's the reciprocal of sine. Sine is opposite over hypotenuse. So cosecant is hypotenuse over opposite. Very, very cool. Number 28. I want to draw a first quadrant angle. First quadrant again because x is positive. A first quadrant angle named u. Drop a vertical line down to the x-axis and label this triangle so that the sine of u would be square root of x squared minus 9 over x. Sine is opposite over hypotenuse. So that means the side opposite u is square root of x squared minus 9. And the hypotenuse is x. This one may be just a tiny bit harder to find this adjacent side, but I bet if you squinted, you could figure it out. You know that this missing leg is going to be the square root of this squared minus this squared. What does that mean the adjacent side has to be? 3. This side would be square root of x squared minus 9. That's correct. So here's our angle u. And now we just want to find cotangent of u. Tangent would be opposite over hypotenuse. So, no, it wouldn't. Goodness. Tangent would be opposite over adjacent. So cotangent is adjacent over opposite. And you don't have to rationalize that. They probably haven't in the back of the book. They've probably left it 3 over square root of x squared minus 9. All right, very last one for today. Number 30 is the cosine, not just the cosine of inverse tangent of x, but the cosine of 2 times inverse tangent of x. Well, the inverse tangent of x is just some angle u. After I draw a picture of it, I'm going to need to find cosine of 2u. That's going to take one of my double angle formulas. First, I need to draw this angle u. And label this triangle in such a way that opposite over adjacent is x. That means opposite is x, adjacent is 1. Sure enough, the tangent of u would be x over 1. That's the angle we're looking for. That means the hypotenuse has to be the square root of, you could either say 1 plus x squared or x squared plus 1. And then again, we're not looking for cosine of u, we're looking for cosine of 2u. And that's one of the double angle formulas, that there are 3 different formulas that we can use for double angle formula for cosine. And regardless of which one you use, the answer should all simplify to the same thing. So I'm just any, miny, miny, mo, this middle one looks good. I'm going to say cosine of 2u is 1 minus 2 sine squared u. Then I only have to extract one trig value from this formula or from this picture. I just need to say sine of u would be opposite over hypotenuse. And the formula is 1 minus 2 sine squared u. So simplify that as much as possible. Square the numerator, and then multiply 2 times x squared. Square the denominator. It's just x squared minus 1. Now, it would be okay. I'm so happy if you got that far. That would be fine. If you used one of the other two double angle formulas for cosine, you might get an answer that looks different than this. But I bet if you wrote that 1 as x squared minus 1 over x squared minus 1 to get a common denominator, and then subtracted the second fraction from it, you would get the same answer that you would use if you used a different double angle formula. That would be negative x squared minus 1, 1x squared minus 2x squared, negative 1x squared minus 1 over this. Hey, are those just opposites? Can you just cancel them and leave a negative 1? The x squares are opposites, but the 1s aren't opposites. The only other thing you could do to that is factor out a negative 1 and just have it out in front of parentheses or in front of the fractions or whole fraction. Either of these three answers would be fine because you've done all the hard work. Alrighty, that should get you able to complete the 6.6 homework, which is 1 through 31 odd, and then just practice graphing your three main inverse trig functions: inverse sine, inverse cosine, and inverse tangent. All right, that's it. Have a great day.